everyone! You are listening to Through Time and Clades. My name is Joan,
And I'm Albert.
and we are back for another news episode. This time around, we're going to be focusing on fascinating news and discoveries for June of 2024. So this is going to be a singular month episode this time around. But before we jump into that, Albert, how have you been?
I haven't been too bad. I've been quite busy with a number of different projects, but things are going well, I think.
Yeah, mine's been pretty good too. Not a whole lot to report. My sister Julie came to visit for Independence Day, which was always pretty nice. I had seen her since the Christmas time,
Oh, wow.
and otherwise, I've just been, you know, keeping busy at work, and then making my art and working on the show in my spare time, and catching up with things. I got a pretty good, steady rhythm and routine going at the moment, and it's been pretty nice. It's been helping out a lot with bills and stuff, so I'm always happy about that. But yeah, no, we definitely have a good size episode for y'all today.
Yep.
Um, in fact, we have quite a bit of follow up that we get to cover for a change, which I always appreciate having. So unless there's anything else you wanted to add, we can go ahead and jump into that.
Yeah, let's do it.
Alrighty, so let's go to the next slide now. And so we got a couple stories here that I'll highlight in brief. So first of all, when we celebrated our 1 year anniversary way back in August of 2021, we got a question from my sister Julie about how different cultures from around the world interpreted fossils and whether they inspired myths. One of the most famous proposals on this front is the idea that fossils of Protoceratops, the ceratopsian dinosaur, inspired the myth of the griffin in ancient Greece. According to the model, which was developed by a folklorist named Adrian Mayer in the 1990s, word about fossils of Protoceratops, which were often associated with gold deposits, traveled from Mongolia along Central Eurasian trade routes, reaching the Greek city-states and spawning tales of the infamous bird-lion creatures. Now, paleontologist and paleoartist Mark Whitten has written extensively on this subject and had expressed criticism about this model. So, as part of this follow up, we'd like to highlight this new June paper by Whitten and co authored by Richard Hing, which fully fleshes out their concerns. Basically, Whitten and Hing argue well, data do not support a connection between Protoceratops and griffins. The earliest documented evidence of griffin mythology actually originated from Southwest Asia prior to 4000 BC and spread north into the Aegean by 800 BC and Persian occupied Central Eurasia by 500 BC, which does not support the proposed transmission of griffin mythology as stated beforehand. On top of that, the association with gold mines falls by the wayside when you realize that the actual distance between the fossil deposits and the gold mines are many hundreds of kilometers apart.
Hmm.
And add to this the real lack of similarities between griffin depictions across time and the dinosaur itself. Uh, the connection becomes broken, or at the very least, much less convincing than it was beforehand. And so I thought that the final lines of this paper uh, were really were really well said. And so I want to highlight those by Whitten and Hing, who state there is nothing inherently implausible with the idea that ancient peoples found dinosaur bones and incorporated them into mythology, be that of the griffin or any other folkloric creature, but such examples must be rooted in realities of history, geography, and paleontology if they are to
Hmm.
rise above the level of mere possibility. And so I know during our 1 year anniversary, upon looking at Witten's earlier writings and his doubts about it, I think it's nice to see this actually in a formal scientific paper.
Hmm.
And
Hmm.
hopefully we can kind of go away to finally putting that idea to rest because it often pops up every now and then. in popular media or even in like scientific circles online. Um,
Hmm.
so that's our first follow up. Albert, do you have any comments about this?
Not much that you haven't said, but yeah, I'm in full agreement there. It is really interesting to see this actually become a paper because I remember seeing Mark Whitten's blog post about this topic. It is always kind of fun to see these kind of musings morph from a sort of informal context, a blog post, albeit a well-researched and well-informed blog post, into kind of scientific, technical, peer-reviewed literature. So I know of a number of stories like that in the field of paleontology, and it's always really interesting to see. So yeah, I was also very happy to see this paper published.
Definitely. And of course, the wonderful art here on the left, which accompanies this area, that of course that is a Mark Witt piece
Mhm.
showing a more traditional looking griffin with some Protoceratops fossils. So that's pretty nice to see. I kind of like the I feel like there's hints of a sphinx cat lion
Yes.
in this design, especially with the wrinkles. That's kind of neat. That's a neat take. Um, right. So moving on. So our next follow up on the number of orca species, and in particular, the most recent proposal by Moore and et al. 2024 that the resident and Briggs orcas of the eastern North Pacific Ocean are their own distinct species. Well, just this month, the Taxonomic Committee of the Society of Marine Mammalogy has finally put out their response to the proposal,
Hmm.
and they had this to say. No, well, more specifically, they stated that the evidence that Morin and colleagues used to separate the two populations as their own species was actually not strong enough, and that these giant dolphins should remain as a single species for now, that is, Orcinus orca. Um, on one point, there is apparent interbreeding between these populations that muddles their distinctness. And on another point, the initial analyses did not fairly sample evidence from others of the Briggs type, as well as the offshore populations, to really make sure the results are not an artifact of poor sampling. So, in the end, while the committee have decided not to go forward with this proposal, they did at least offer a sort of compromise and recognized the two Eastern Pacific orcas as their own subspecies. So the residents would then be Orcinus orca ater, and the Briggs would be Orcinus orca rectopinus. So recycling the species names into subspecies names. Now, of course, this is not necessarily the last word, and maybe new analyses will go back to the old proposal or keep this one. But for now, it seems we're back to there just being one type of orca after all. Uh, Albert, do you have any comments about this particular development?
Yeah, I mean, it is interesting to see these kinds of decisions made by taxonomic committees, and it is interesting on one hand because not all types of organisms have like these taxonomic committees like governing their taxonomy. We do, for example, have multiple groups of committees out there trying to establish the taxonomy of living birds, for example. In fact, this might be one of the best known examples. It's probably in birds because bird watchers like to follow these committees and say, oh, so based on these decisions, how many species of birds have I seen? Because that might change depending on the classification. But that's not the case for all types of organisms. Like there aren't any central taxonomic committees for, say, extinct dinosaurs, and so there's no central authority you can point to and say, okay, so this group recognizes these particular species as valid, and so it is always interesting to see like this. That there's this sort of extra level of taxonomic authority, like kind of reacting to all the new studies on taxonomy that come out. especially because I mentioned that there are multiple taxonomic committees doing like living birds, right? And like these different committees don't always agree with each other, and so depending on whose list you follow, you can have a very different list of species of birds that you've seen. And it seems that in this case, with the marine mammals, the new orca study, while very thorough, was not sufficient for them to change that particular classification, which I mean. I think it's not being a researcher in cetaceans. I mean, it seems relatively fair to me. I do think like the points about how like the other populations of orcas in the world they need to be considered and all of that. I think that's probably fair to at least wait for new data. Obviously, in all cases, when it comes to these decisions, this is definitely not the last word on the taxonomy of these organisms. It is just a reflection of the state of our knowledge and research at the moment. And so I think if they want to wait to see more data become available, I think that's perfectly fair. And I'm sure that this has created enough of a buzz in the marine mammal research community that we probably will be seeing more studies on this very soon, at least soon enough by scientific standards. I wouldn't say I'm necessarily surprised by this outcome, um, but it is pretty interesting to see that they've decided to be relatively conservative in light of what we discussed regarding this new study.
Right. And as I mentioned, going through the history of orca species proposals, like this, there are precedents for this sort of thing. Researchers have in the past have proposed species, and different communities have basically come to an agreement that the evidence is just not right enough to say yes or no. And so to be safe, we just keep things as they are with one orca. And granted, admittedly, Morin et al.'s study was probably the most thorough that I had seen when scouting the older papers,
Right.
and certainly they did their best to at least account for all of the past proposals to make sure that nothing was missing. So, at least on their front, I think that they had a logically good proposal going forward.
Hmm.
But definitely, like there was data that was missing, and really like you said, it'd be good to take into account the entirety of orcas around the world, make absolutely sure, because goodness knows species get around a lot, and with this recent surge in DNA research, we are finding all sorts of interbreeding and population movements with different organisms of similar size. So it could be much more complicated than it's looking here.
Hmm.
It's a very good question. Um, but certainly, something like this just goes to show that just because a new paper comes out with a new result, that does not mean that now that is established science. Everyone's got to follow along with it. It's
Right.
like it's the big shot on the block. No, science is a process, and these papers that come out are ways that further that process, get conversations going, get more research going to further understand what exactly is going on out in the world. And so there are going to be high standards like this. So it's interesting to see, especially considering how recent this was. Like, it feels like that paper had just come out, and already we had this big committee coming and having a response. And that's
Hmm.
how these things happen often in science. Certainly, uh, no surprises here. Um, Alrighty then, let's move on to the next slide. And I have one more follow up. And then, Albert, I know you have some follow up coming up too. So, right. We have covered the ongoing discourse surrounding the origin, evolution, and status of the Australian dingoes and New Guinea singing dogs many times on this show now. And so it felt appropriate to share this recent paper from June by Yassine Sulimi and colleagues. This is a significant update on an earlier 2020 paper by Zhaozhe Zhang and colleagues, which was the first to use whole genomes in a phylogeny of Oceanian dogs, which we've covered before on this show. Now, in this new 2024 study, almost all the genomes this time around came from ancient specimens that predate European colonization on the islands, so as to remove worries about contamination of modern dingo and New Guinea dog genomes with foreign domestic dogs. Now, the team's genetic data showed that the populations of Oceanian dogs had indeed been diverging into different lineages long before 2,000 years ago, which was also the age of the oldest archaeozoological specimens, having diverged between 8 and 3,000 years ago, which was in line with earlier results. Within Australia, dingoes can be divided into at least two subpopulations, those in northwest Australia and those in the southeast. Now, the phylogenetic models, which I show here on this slide, could not show a preference between several hypotheses for the arrival of dogs in Oceania based on the data. So either dingoes arrived in Australia once and split into these two groups, or dingoes arrived at two intervals into Australia after splitting off from the New Guinea dogs, or the New Guinea dogs are only related to one of the dingo subpopulations, or the third option, but with additional gene flow either from Australia into New Guinea or vice versa. So, yeah, this may not sound like a major clarification, but it certainly gives canid researchers places to conduct further research, especially with hopes to include native dogs of continental and island Southeast Asia, which genetic trails have pointed towards Australia and the Pacific Islands. So perhaps we can gain a lot more insights and maybe even better chart the path of dogs into Oceania. But it is interesting to see just how many different models the team could come up with
Mm.
that seem to match the genetic data that they had. Um, so this is kind of an exciting and confusing study, admittedly. I'd love to hear your thoughts about this sort of thing.
I'm more or less with you there. Like, this sounds like an extremely interesting study. Like, I know this has been like a big problem, in, the study of kind of the history of dogs, for a long time, and we've certainly discussed that before on the show. Um, it certainly looks like they didn't find any definitive answers, which is often the case in science. But I do think it is very interesting to see them narrow things down to these several different models and possibilities, all of which would be very intriguing, no matter which one turns out to be the case.
Oh, for sure. At the very least, like it definitely adds pretty strong confirmation that the dingo and the New Guinea singing dog do have something to do with each other,
Mhm.
evolutionarily speaking. These are not just convergences of your typical wild dog type from which all domestic dogs ultimately originated from. Um, yeah, I'd love to see more research into this, and of course, then the implications there. Well, okay, if the New Guinea dogs are only, if dingoes are only partially related to the New Guinea singing dog by like one population or not, well then you could, I guess, arguably call New Guinea dogs New Guinea dingoes. I
Right.
mean
Yeah.
or consider them all the same breed, or population or what have you. Um, yeah, but when it comes to domestic species, like the terminology for groups can get a little bit muddied. Um, Goodness knows, in domestic dogs, while they can be divided into several lineages going into the deep past, I mean they've been interbred with each other so much
Hmm.
that you can't really divide them further from their subspecies label without getting things very confused and messy quickly. Um, but that's all part of the fun. Um, Alrighty then, let's move to the next slide now. And Albert, I'll give you the floor. I see we have a very fun follow up this time around here.
Yes. So, for those of you who have followed us for a while now, I suppose, you might recall that we once did an episode on old websites about paleontology that have since gone defunct for some reason or another. Um, yeah, that was a really fun episode to record. Also, one of our longest episodes ever. But no, it was really cool. I think it was really fun to do. And in one of the many websites that we discussed were the archives of the dinosaur mailing list. Yeah, if you haven't been around on the internet for very long, you might not even be all that familiar with mailing lists because they're often considered a very, I guess, archaic form of online communication. Basically, what a mailing list is like it's a system where you can sign up to this mailing list. You can enter your email into it. They add your email to the list, and then any emails that anyone in the who is on the list sends through the list will end up in your email inbox. And so it's basically a way to sort of join a community of people and receive their messages in your email. And the dinosaur mailing list was one such group that started all the way in the 1990s. Yeah, so it's been around for a very long time, and it continued all the way until this year. Now, the reason that we included the dinosaur mailing list in the episode about defunct websites was not because the mailing list itself had died off, even though activity has slowed considerably in recent years. Um, but instead because the public archives that were archiving all the messages that were sent through the group um, were shutting down. Unfortunately, people have since made backups of the website, and so you can still access those old archives, but the original site that was hosting them, it has shut down. Um, and at the time, we mentioned that some people have kind of gotten this confused, that they think that the archive shutting down meant that the entire mailing list was shutting down, and people were saying, "Oh, the mailing list is dead now," which at the time was not true. So it was like basically stop telling people that the dinosaur mailing list is dead because it's not actually dead. However, earlier this year, we received the news that the mailing list itself actually would be shut down for real, and that's because the university that
Mm.
was hosting it, I think it was the University of Southern California, if I'm not mistaken. The university was deciding not to host it anymore. And so um, there was a real risk that the dinosaur mailing list itself would actually cease to operate anymore after that. Fortunately, we did have advance warning that this was going to happen, and so some of the members of this got together and decided to kind of resurrect it in a way. And so before the mailing list shut down for real, they set up this new group on Google Groups called the Dinosaur Mailing Group, and said, okay, if anybody on the dinosaur mailing list wants to continue receiving similar messages in a similar type of community to the dinosaur mailing list, then please join this Google group and you can do all of that. And we can continue as if nothing happened, basically. And that's what a lot of people, including myself, did, was that we signed up to this group. In May, I believe, in late May, the University of Southern California did indeed pull the plug on the dinosaur mailing list. And so it's not around anymore. If you were signed up to it before, you won't be receiving any more emails since then because yeah, they just stopped hosting it. However, if you've signed up to the dinosaur mailing group, then yes, you will continue to receive all these different emails that were regularly sent through the list because a lot of the mailing list regulars have signed onto the mailing group and have continued to kind of post on it as if it were still the old dinosaur mailing list. Um, and so the dinosaur mailing list kind of continues to live on. The people who run it now are a different team of people, or slightly different. One of the original co-owners is still on it, but the way that it works is basically the same. And as a nice bonus is that Google Groups, it does like automatically archive all these messages that are sent to the mailing groups, and so that means that even if you're not a member of the dinosaur mailing group, you can still go on to this group page that I've posted a screenshot of here, and we will be putting a link to it in the description below and see what messages have been sent to the group, even if you're not directly a member of the group. So that's pretty useful. And yeah, it's very cool to see the dinosaur mailing list continue to live on even after its eventual like demise, or so to speak. So this was a pretty good follow-up to what we discussed in that particular defunct websites episode.
That's fantastic. Oh my gosh. Well, for one, I'm very happy to see that we have the spiritual successor that's not only available, but basically continue doing what the original mailing list had done.
Mhm.
And so it's almost like it never really left.
Yeah,
It,
exactly.
it's just found a new skin, new life, new address. That's fantastic.
Mhm.
Um, Now, just to be clear, now that the old dinosaur mailing list is gone, like, is it still available to like go on the Wayback Machine and pull up all the old messages and stuff, or is it like gone, like it's been scrubbed?
Yeah, that's a good question. So all of the messages up until the archives went down have been saved by other people and are available online, which I think we might have mentioned in the episode that we discussed this on. However, the newer messages, like between that time and until the death of the original dinosaur mailing list, I think are not available in any public format. At least that's my recollection. To the best of my knowledge, that's the case. So there is like a segment of missing history, I guess, that's not really available to the public, as far as I'm aware. But yeah, if you were subscribed to the mailing list within that time, then you probably did receive like all the emails from that time period. But yeah, I don't think there's been a public archive of that made.
Gotcha. Yeah. Well, I guess in that case, like if the people save the emails from that time, then I guess that is one way to keep the records,
Right.
if the emails don't work anymore. Um, I'm sure people were working on that too. People are pretty diligent about saving things online.
Yeah.
I've come to discover. So, but either way, like this is pretty nice, and I can't wait to see what kind of new discussions come about from the dinosaur mailing group, and who knows, maybe in 20 years we'll be looking back on some of these classic messages on the dinosaur mailing group like we did with the mailing list and kind of
Mhm.
see things that were teased or previewed or talked about, um, which is always kind of fun to see.
Yep.
Well, that's pretty exciting. So that's our follow up for right now. Again, a lot of really neat things. I definitely want to try to do more follow up for the show because, I mean, for one thing, it helps kind of show how science is an ongoing conversation,
Mhm.
and also just to keep continuity between these news episodes, um, which helps kind of cohese the show a little bit more. Um, but alas, now we have to go to our news stories themselves. So, as per the format of our 1 month news episodes, each of us have two stories that we're going to cover. And Albert has the floor with your first story. So, why don't you
Mhm.
fill us in on what we got here today?
Yeah, all right. As a very in character pick, our first news story for me is about birds. And so this one is a pretty fascinating one, I think. So it is about the air sacs of birds, which are part of their respiratory system. And if you know anything about birds, you've probably heard of this before, that birds have air sacs kind of connected to their lungs. Um, and that's because they have a very complex and very interesting respiratory system, a very unusual way of breathing, at least compared to us. If you think about how you breathe or how other mammals breathe, it's relatively simple, at least compared to a bird system. So when you breathe in, the fresh air comes into your lungs and your lungs inflate. And when you breathe out, the stale air kind of goes out the same way that the fresh air came in, and your lungs deflate. And it just kind of does this over and over again in a cycle. Um, and so that's a relatively straightforward to understand. However, in a bird, what happens is quite different. The lungs of birds do not inflate and deflate. They pretty much remain static, and they're kind of attached to the top of the rib cage in birds, or they're on the inside of the rib cage, but attached to, like the top of it, like against the back. Um, and what happens is that instead of the lungs inflating and deflating, birds have a system of air sacs that inflate and deflate instead. So when a bird breathes in, the fresh air comes in, and some of that fresh air goes into the lungs. However, another portion of the fresh air goes into the air sacs, and it is held there for a little bit. And when the bird breathes out, the stale air in the lung goes out, and it goes into another set of air sacs, whereas the fresh air that was held in the air sacs before is pumped into the lungs. And so this gives birds a very efficient way of extracting oxygen because they can extract oxygen when they breathe in as well as when they breathe out, which is very different from our system when we only get fresh air when we breathe in. And on the next time the bird breathes out, the stale air that was held in the air sacs from before gets expelled out into the outside world. Um, and so that is a very interesting kind of way to shunt all these different portions of air around in the respiratory system, very different from ours. And to be clear, like the air sacs of the birds do not extract oxygen or like exchange stale air. Like the air is just held there for temporarily during the breathing cycle, and it's the lungs that do the actual gas exchange, just like it is in us. And they have this very complex system of air sacs that runs throughout their body. And the air sacs themselves have like extensions of like smaller air sacs coming off of them. Um, and certainly these air sacs have a very important role in breathing. However, we have known for a long time that in many birds, at least, the air sacs can potentially also have other functions, like they can enhance vocalization, for example. Birds can use them to help make sounds. In some cases, they might be able to help the birds inflate display structures and such. And the system of air sacs, like especially the smaller extensions coming off the main air sacs, extend into the bones of birds. And so this is actually the reason that birds have hollow bones is that they have these extensions of the air sac system that hollow out the bones. That's how they're able to have hollow bones. We know that in a lot of non-bird dinosaurs, um, they probably also had these air sacs and probably had a similar breathing system because we find the little holes in the bone where these air sacs would have gone into, would have invaded, as we say. So this is very cool. So this is an adaptation that birds have retained for a very long time from like non-flying ancestors. And of course, it does make them very good at breathing. But this new study found kind of a new function of the air sac system that we didn't really know about before. I mean, people had speculated about before, but we didn't have like a lot of direct evidence for. Um, and I think this study was really well done, actually. So specifically, they were investigating a particular structure in the air sac system, which is one of these like smaller extensions of the air sac system that is called the subpectoral diverticulum. A long name. In fact, in most of the paper, they just call it the SPD for short. Well, understandably. This is a smaller air sac that comes off one of the main air sacs, which is called actually, it should be called the interclavicular air sac. I have a typo on here. Um, the interclavicular air sac is found in the chest cavity of birds. It's basically associated with the wishbone of birds. And that's why it's called the interclavicular air sac. It's because the clavicles are the collarbones, and the wishbone of birds is generally thought to be basically the two collarbones fused together, although there is some debate about that. This is not the time to go into that, however. In any case, the interclavicular air sac fits in the chest cavity, kind of between the two main branches of the wishbone, and the subpectoral diverticulum comes off of that. Um, and you can see in this figure here, this is a scan of a hawk skeleton. Where in the leftmost image you can see all of the air sacs like inflated, and those are the blue things you can see like distributed throughout the skeleton. You can see that the air sacs are very tightly associated with the skeleton, and they fit into like a lot of the crevices and such in the bones. Now, the other two figures kind of show the subpectoral diverticulum just by itself. And so you can see the subpectoral diverticulum inflated in the letter B here, and you can see how it fits into the chest cavity. And then it is deflated in letter C. So that's what it looks like when there isn't really any air in it. So this is a very interesting structure in the respiratory system of birds because not all birds have a subpectoral diverticulum. And so, what the authors did first was that they looked at a bunch of different bird specimens from all across the bird family tree to see which birds had the subpectoral diverticulum and which did not. And what they found was a very interesting pattern. It turns out that nearly all the types of birds that they found that regularly did soaring flight specifically had a subpectoral diverticulum, with only one or two exceptions among soaring birds that did not have one. Nearly all soaring birds that they looked at had this unusual extension of the air sac system, whereas none of the non-soaring birds that they looked at had this structure. So there was a very clear pattern in which birds had this and which ones didn't. Now, not all soaring birds are close relatives of each other. This is a behavior that has kind of been adopted by birds many times independently. And so this suggests that the subpectoral diverticulum also evolved at least 7 different times independently, according to the results found by these authors. And so soaring flight is a method of flight where birds basically um, don't create their own lift by flapping their wings, but instead kind of gain lift from kind of external energy sources in the environment. Oftentimes, this is kind of rising columns of warm air called thermals. Like as the sun warms the ground, it creates these rising columns that birds can kind of fly upon without flapping their wings. So if you've ever watched things like vultures or hawks a lot, you can often see them doing this. Um, this is a very kind of energy efficient way of flying. And so the authors wondered whether or not the subpectoral diverticulum had anything to do with kind of the mechanics of soaring flight. Did it help these birds soar in some way, if it's only found in soaring birds and in almost all soaring birds at that? Um, so first of all, what they did was they observed the structure in some living birds. So like they examined some living birds and sedated them, um, and kind of did a scan of their insides to see what was going on with the subpectoral diverticulum in a living bird. And what they found was that birds that had this structure could voluntarily kind of collapse the subpectoral diverticulum, like expel all the air from it. The subpectoral diverticulum comes in pairs, so there's one on each side, and they could collapse one at a time or both at the same time, and it didn't matter. Like either way, these birds could breathe just fine, even when the subpectoral diverticulum was collapsed. And so clearly, this structure was not essential to breathing in these birds. So how about a possible function in kind of soaring flight mechanics then? Well, to test this idea, what the authors did was they used computer modeling to try and test this idea. Because if you want to observe like an actual living bird, like soaring out in the wild, and then measure like what was going on or observe what's going on with the subpectoral diverticulum inside it. Um, as you might imagine, that's basically not practical in any way. Um, so yeah, they couldn't actually do that, but they did do the next best thing, which was they took scans of these birds and then modeled how the subpectoral diverticulum would influence the muscles that were associated with soaring when it was inflated versus when it was deflated. And what they found was that it is quite likely that having an inflated subpectoral diverticulum improves the ability of these birds to soar. So how does this work? Well, if you think about what a bird does when it's soaring, what it's doing is basically holding the wings out to the sides horizontally and keeping them still. So it's not flapping with them, and it wants to like hold them out to the side so it can get like the maximum amount of lift possible from like the air currents below it, right? Um, Now think about this. If you're holding your arms out to the side for a very, very long period of time, you're going to get tired very quickly, right? And so the muscles of soaring birds are actually specially adapted to for them to be able to maintain this posture for a very long period of time. And it turns out that the subpectoral diverticulum might actually help with this. Um, because when it is inflated, what it basically does is that it causes the muscles to stretch a little bit more and making them longer. And what this does is that it improves the leverage of the muscles that prevent the wings from going upward. So, because the bird needs to maintain the wings in a horizontal posture, so it has these big chest muscles that are pulling the wing downward to kind of maintain this, and so preventing the wings from flipping up. Um, and it turns out that when the subpectoral diverticulum is inflated, according to their computer models, it can actually have this stabilizing effect and it help make the muscles more efficient at maintaining this horizontal pose of the wings. Um, and so this is really, really cool because first of all, how thoroughly they investigated this topic. Like they looked at dead birds and living birds and computer modeling, um, and they found this very clear correlation between having this structure and a certain type of behavior, locomotory behavior. And furthermore, they were able to demonstrate with their modeling studies that this type of structure very likely has a benefit to this type of locomotion. It gives us a very nice example of the avian respiratory system having a function other than respiration, in this particular case, enhancing flight mechanics, which is something that, even though some people had suggested might be the case before, had not really been demonstrated in this way. And so this is, I think, a very fascinating and impressive paper. And quite rightly, it got published in Nature, which is one of the top scientific journals in the world. Um, and so, yeah, really cool paper. And I thought that this would be a very good opportunity to discuss it. Do you have any thoughts?
Yeah, I mean, I would agree with you completely. It really, honestly, kind of changes my perspective a little bit about seeing soaring birds like this. Because where I grew up, I see a lot of turkey vultures and black
Yes.
vultures, and those are very common soaring birds. And I mean, it always looks effortless the way that they do it, but it's easy to forget that a bird in flight is still using its energy like we would running or
Mm,
care or lifting something. So it's fascinating to know now, or at least suspect really highly, that there are organs at play that have adapted to this behavior to make it more efficient and certainly easier for birds
mm,
of these types to soar uh, than if it hadn't been there at all. It's almost like the air sacs have turned into a kind of tendon
yeah,
that locks in place and
exactly.
allows the wings to keep that position because that is some remarkable adaptation there. Um, that's really neat to see. Yeah, I really like this paper a lot, and I definitely am interested in taking a look at it on my own time for sure to kind of see more because I'm sure there are other uh, like scans like this of all the different soaring birds that they examined
Yep.
um, to kind of see like the dimensions of the diverticulum and how exactly it's held out on the bird. Um, that would be neat to see. Yeah, this was very good. Um, Alrighty, so let's move on now to the next slide, and we'll do my first story
Mm,
for the month. So this paper comes from Chunxiao Li and colleagues. Um, but before we discuss that, I think it will help our viewers if I went over a rough overview of the evolution of the elephants and their relatives, the clade
yep.
proboscidea. We've talked about proboscideans many times in past episodes, but I feel like I've done little to outline what we know about this group and how it evolved, because among fossil mammals, it's probably one of the best fossil records out there. Um, so let's try to remedy this here. So, among the placental mammals, the clade Afrotheria encompasses a collection of bizarre and fascinating species that seem to have evolved within the African continent at some point during or after the Cretaceous mass extinction event 66 million years ago. This, of course, includes the Sengis or elephant shrews, the Tenrecs and the golden moles, the aardvarks, and then there's a clade called Penungulata, or the almost hoofed mammals because these animals evolved hoof digits independently from the true ungulates like horses and cattle. Based on the most recent phylogenetic study available, that by Gaoming Liu and colleagues, which was first printed last month, though available since March, the closest living relatives of the Proboscidea are the Hyraxes, or Hyracoidea, and then followed by the sea cows, or Sirenia, whose common ancestor may have been a semi-aquatic animal. We have yet to find fossils of any Afrotherians similar to this common ancestor, but we at least have some great representatives of very early fossils. Now, to date, the oldest Afrothere is a genus called Ossipaya, which inhabited present-day Morocco on the shores of what was once the Tethys Ocean, but is now the Mediterranean, around 61 million years ago. While it may or may not have been especially close to the penungulates, and was probably more arboreal than semi-aquatic, it still has telltale features that unite many of the Athypheres, like a large nasal cavity and specific details of the molar and incisor teeth. You can find a life reconstruction on the head on the far left of this slide, which contains a phylogeny of Proboscidea itself, which is designated by the PRO here on the left. Now, from there, the oldest Proboscidean proper, which is only about a million years later in date, is Erytherium, also from Morocco. With this animal, we see more characteristic penungulate traits, especially the four rounded cusped molars, and more characteristic proboscidean traits like forward facing eye sockets. Following this animal 59 to 56 million years ago is Phosphatherium, and also from Morocco, which began to have more differentiated molar teeth than its earlier relatives, with cross chests or enamel ridges that are typical of living elephants. I also have a restoration of this animal pictured on the left of this slide, and right away you can tell that these early proboscideans did not look particularly elephant-like early on in the lineage. They would have had wide snouts and perhaps fleshy lips for eating leaves, but these were not. There were no visible tusks, nor a trunk present on the face. They would have honestly looked right at home with many of the other now extinct lineages of Paleocene and Eocene mammals. It's not until we travel further forwards in time that we find creatures like Numidiotherium and Moratherium that the elephant-like nature of these animals begins to shine through. By their time, which is between 53 and 37 million years ago, proboscideans had expanded across much of North Africa, reaching present-day Egypt, and they had grown in size towards something comparable to or a little larger than a tapir, about 3 meters long and weighing about 235 kilograms. If the image to the left is any indication, animals like Moratherium would have been rotund with squat limbs, indicating that they were still quite semi-aquatic. And we even have isotopic studies that also seem to confirm this, showing that they consumed a diet of freshwater swamp and river plants. It's in the face that we especially need to draw our attention, because the skull of these proboscideans actually begin to resemble something like a proto-elephant. The cranium is more risen, the eyes are more forward, and the nasal cavity is more risen on the face. And both the upper and lower incisor teeth are more elongated and tusk-like. And the combination of these traits suggests that Moratherium and its fellows had something like a fleshy upper lip, shaped into a small proboscis, which is the beginning of a trunk which gives the group its name. Eventually, by 30 to 25 million years ago, the clade Proboscidea began to rapidly speciate and spread across Africa. The first lineage to branch off were the Dinotherids, probably one of the most bizarre of the clade. Over time, their upper incisor tusks were lost, while the lower jaw and its incisor tusks curved and started pointing downwards, appearing like double hooks. Now, why would a mammal like Dinotherium, which is pictured here, need something like this? Well, tooth-wear studies suggest that these animals were eating softer forest foliage with their vertical shearing teeth. And while the jury is still out on the lower tusks, the most cited hypothesis is that they were literally hooks. They would be used to grip onto branches and then pull them closer to the upper lip, which cranial studies suggest had formed a trunk of some size and shape so as to better reach the leaves. Now, Dinotherids, it should be stressed, were unique animals, and there's really nothing to suggest that they would have looked exactly like living elephants with just a different face. But the link with later proboscideans and the true elephants was very strong, for the common ancestor of this and all the others had developed the complete enamel ridges along the molar teeth. Now we come to the start of a clade called Elephantiformes. In these, the upper tusks are more fully formed, and the lower jaw started to elongate as well, particularly a region towards the front called the mandibular symphysis. Keep an eye on that term later. The next lineages to branch off from this point are genera like Phiomia and Paleomastodon, which is pictured here towards the middle of the slide. These animals were much larger now, comparable in size to a cow or rhinoceros. These were far more elephantine-like animals, but it isn't until the subclade Elephantomorpha that you start to find representatives that you'd be forgiven were thinking were true elephants. These are, of course, the Mamutids or the Mastodons, which had evolved by 24 million years ago and were some of the first proboscideans to have evolved a proper elongated trunk with upper tusks to match. Later forms like Zygolophodon and Mammut even developed super elongated tusks that would have been almost as long as the body. Now, like most of the earlier proboscideans after Moratherium and their kin, Mastodons seem to have been foragers of forest-type vegetation, chewing on leaves and nuts with round conical cusped teeth, which give them their name. By 19 million years ago, the African and Arabian continental plates were pushed into the Eurasian plate, and those lands were finally connected. This allowed many species to move interchangeably between them, and the proboscideans were those that really took off. Both the dinotherids and the mastodons expanded into Eurasia and very quickly reached Europe and the Americas almost a million years later. Other proboscideans would make the same journeys, which brings us to a critical point of relevance for my new story today. After the mastodons split off, there was a number of different proboscidean clades that began to branch out and radiate between 20 and 11 million years ago, and these have been colloquially known as gomphotheres. Now, originally, Gomphothere was a scientific term for a specific clade of proboscideans, which had greatly elongated their lower jaws into an almost shovel-like shape, often with corresponding upper jaws and tusks to match, which would have given some of these animals a very big, wide mouth that would probably uh, put a crocodile to shame. Uh, but we now know that some of the Gomphotheres were ancestors of the clade Elephantoidea, which houses the true elephants, which includes the mammoths, which are sister relatives of the Asian elephant, and the stegodontids, which is a now extinct group, which elongated their upper tusks so much and closed them so close together that the trunk in life may not have been able to rest between them, like in most other elephants. So Gomphothere has now become a catch-all term for that grade of elephantomorphs besides mastodons and elephantoids. And the big question about Gomphotheres is their place in elephant physical evolution. Based on the skeletal evidence from fossils, we have a very rough idea of when the trunk evolved and when the lower mandible evolved in these animals. But it hasn't always been clear when the trunk eventually replaced the lower mandible as the main food collecting organ, as seen in living elephants and their relatives. This extreme longirostrony is exemplified by many of the Gomphotheres, like Platybelodon and Gomphotherium proper, which are also illustrated here on the slide. And that's where Xunxiao Li and colleagues come in. But before we move on to the next slide, Albert, do you have any comments on the wide scope of proboscidean evolution?
That was a great overview, and it's always fascinating to look at the fossil record of elephants and their close relatives because today we only have three living species, right? And to see that they had this huge lost diversity and disparity in the distant past, and in some cases, the not so distant past, it's just amazing. Definitely one of those things that kind of encourages us to conserve our living elephants because they've come a long way, really.
Absolutely. And definitely want to stress that like proboscideans almost had like free reign of most of the world's land
Hmm.
surface for until relatively recently. I know in some older literature, I've seen the quaternary called the Age of Mammoths because you had proboscideans in North and South America, across Africa, and across Eurasia, and very far south into island Southeast Asia, which was once Sunda. Um, they only didn't reach Australia and Antarctica, but given how much they moved, I'm sure it wouldn't have been a matter of time until they maybe one lucky elephant would have made the trip. Um, but there were so many different species and so many that coexisted with each other. Um, these were like megafauna in a literal sense. I mean, these would have been the sauropods of the world until fairly recently, which is a beautiful group of animals for sure. But yes, let's move on to the next slide now, and we'll cover the actual paper that I want to talk about today. So, to clarify, among the Gomphotheres, there are roughly three clades. So there's Chorolophodontidae, represented in the study by Chorolophodon proper, which has lost the lower tusks, but kept the elongated mandibular symphysis, which in this lineage is described as trough-like, and may have held double keratinous structures akin to the soft tissue sleeves of cat claws, which is a very interesting adaptation. Then there's the Amebelodontidae, which is represented by Platybelodon, which have both upper and lower tusks, but the mandibular symphysis is more spoon-like, with the lower tusks flattened and widened, but having a sharp outer edge. And then there's the so-called Gomphotheridae, which is technically paraphyletic with respect to Elephantoidea, and is represented in the study by Gomphotherium proper. The lower tusks are shaped like clubs, but the mandibular symphysis has become much narrower and much closer to living elephants in proportion. It can generally be understood that these differences in mandibular and trunk morphology have to do with food type and processing. And so to find out just how, the team gathered data on a number of gomphotheres at different sites, particularly in northern China, where the fossil record was very good. They wrote down where and when they lived, the types of environments that they had been preserved in, how many fossils of each genus had been recovered, stable isotope data, and so on. Then, in the three representative genera, the team performed two digital tests on their skulls. The first is called a distal forces test, in which the lower mandible is stretched as far as possible and then given a simulated vertical force of 5,000 newtons to see how much it can take from there. And if you look on the slide on these GIFs, the redder areas on the top of these distal forces tests, they show the most stress.
Mm.
Uh, Now, the second test is called the twig cutting test, and it's pretty exactly as it sounds. A simulated cylindrical twig is placed on the edge of the lower tusks in different directions to show how effective the teeth cut into the material. And so, of course, to reiterate, this slide shows example results as GIFs. For the paper includes short videos on all of these tests, which are available to examine. The paper is open access. The distal forces tests are on top, and the twig cutting tests are on the bottom. And of course, to the left, I have Chorolophodon represented. In the middle are Gomphotherium, and to the right is Platybelodon. Now, lastly, the team examined the nasal areas of a modern elephant skull to look for osteological correlates that could be compared with extinct fossil forms. Basically, features on the surfaces of the bones that are indicative of the soft tissues and muscles and so forth that would have been laid over on top of that. See kind of like what sorts of dimensions, shapes, muscles were present in the fossil species. And from all this, the team was able to gather a more accurate interpretation of these gomphotheres' facial morphology and ecology and find some answers to their concerns. So let's jump now to the next slide, and we have kind of the summary of our results posted here. All three Gomphothere clades were well established in northern China during a period of global warming called the Middle Miocene climatic optimum between 17 and 15 million years ago. And many genera were present in the same relative abundance in the fossil record at the time. But almost immediately after 14.5 million years ago, Chorolophodon and Gomphotherium suffered population declines and even regional extinctions, and both continued to exist until about 11 million years ago when they vanished from the fossil record. But throughout this time, Platybelodon only existed in small areas and periodically in the fossil record. But the evidence also shows that it expanded its range widely and even outcompeted other gomphotheres where it lived. Now, this data suggests that climate and ecology affected the range and feeding behaviors of these proboscideans. Um, so, Chorolophodon was found to have had an archaic and less dexterous trunk, like earlier elephantiforms, which combined with a trough-like jaw and lack of lower tusks, only seems to have eaten horizontally growing plants in closed habitats like forests. Gomphotherium seems to have had a modern elephant-like flexible trunk, which provided it with a so-called unspecialized and flexible diet within a number of different environments, grasslands as well as forests. Platybelodon seems to have had a more unique and derived trunk arrangement, unlike living elephants or any of the other sampled gomphotheres, with a lengthy, strong, flexible trunk that worked in tandem with a lengthy lower mandible. Platybelodon was also found to have eaten mainly grasses, within a grassland environment, as a model where the animal is using its trunk to pull down branches or trees wouldn't work, as the mandibular synthesis would then be made useless. So, looking at the wider data on these gomphotheres, a trend was noted that the lower jaws of each lineage seemed to have reduced in length and the trunk became of greater function independently, which corresponds to changes in the environment and climate after 11 million years ago, which saw the cooling of the Earth's climate and the spread of grassland environments around the world. So, thus, within the paraphyletic gomphotherid lineage, for example, the clade that colonized the Americas and gave rise to genera like Cuvironeus and Nodiomastodon um, have little to no expanded lower jaw and clear evidence of a long, flexible trunk. And even at the start of the modern elephant clade, which is elephant today, this trend is seen in general like Primelephus and Stegotetrabelodon, where the lower jaw is becoming of less importance as the trunk is becoming more prominent. And so this tells us that the main factor that influenced the shift from long lower mandibles to trunks as the main organ for feeding occurred in response to the shift in global environments between 14 and 11 million years ago, from mainly forested regions to mainly grassland regions. And proboscideans independently proceeded to make that transition. The flexibility of Gomphotherium's trunk and diet in particular is demonstrated in modern times by the living elephants, which are found in a wide range of environments and eat many different plant foods. So, with this study, we can now at least offer a temporal and evolutionary context for when this shift began, and so gave us the modern elephant. And so, I thought this was a very fascinating and lengthy study that was very thorough, and it was nice to actually get some more proper fleshy reconstructions of some of these gomphotheres, which have gone through numerous interpretations in paleo art over the years. It's just something a little bit more accurate and in line with the fossil evidence, which the technology nowadays is so much better, and the sample sizes are so much better that we can actually flesh out these animals more and see how they were actually living in their environment. And also just to see how we got from something like a gomphothere to an elephant. Fascinating transition. So I really enjoyed covering this paper, and I'd love to hear your thoughts, buddy.
Yeah, I agree. This looks like a really thorough study. Um, and I think it's pretty cool because certainly when you look at these extinct proboscideans and things like Platypelodon, for example, or perhaps some of the most commonly pictured extinct Cenozoic mammals in books about extinct life. One of the first things you that immediately jumps to mind when you see them is okay, clearly the jaw apparatus is very different from modern elephants. So what were they using that for? And I know there have been multiple different hypotheses about this over the years. And I think for those of us who go on to continue thinking about these animals, I think another question that pops into mind is when did the trunk evolve? Because that's something that does not directly preserve usually in the fossil record, right? It's mostly consisting of soft tissue. And so it's like, so did all of these extinct proboscideans have trunks or not? This particular study kind of addresses both of these topics. And pulls them together into a very holistic kind of perspective, which is really fun to see. Um, the interpretations seem to make a lot of sense. And it is really interesting to see that there is this trade-off between the development of the trunk versus the lower jaw. Yeah, certainly the lower jaw is one of those main kind of big differences that these animals have from modern elephants, right? And yes, what you mentioned about the influence of the environment on proboscidean evolution too. It's really good to get that kind of viewpoint as well, because we know how the drying of habitats and the expansion of the grasslands were some like the big kind of environmental changes that were happening in the later part of the Cenozoic up to present day, and has often been invoked in um, kind of studies of human evolution, as we know very well. So to think about how it might have affected elephants and to have some evidence for this, I think is really great. It reminds me of this a different proboscidean study that you talked about not too long ago, which was about that kind of the evolutionary dynamics of proboscideans over time and how they might have been associated with various environmental factors. It seems that this study has a piece of the puzzle to that. Um, so that's really great. I think this was a really great study to have picked for this episode.
Oh, I'm very glad to hear that. Yeah, and I agree completely. Um, and so moving on now, I will definitely say that I am most excited to hear you talk about your second news story because this is another one of those that was honestly one of the highlights of the month for me.
Yeah, I would certainly agree with that because that's why I picked the story after all. But yes, I was quite excited to see this study, and so we are going to talk about dinosaurs again, and we are going to talk about phylogeny. So once more, this is not a surprise at all coming from me, but the particular group of dinosaurs we're going to talk about are the ornithischian dinosaurs, or the so-called bird-hipped dinosaurs, which does deviate a little bit from my usual topics of focus because um, this is kind of the obligatory thing that you always have to mention when you introduce the bird-hipped dinosaurs, is that even though birds are dinosaurs, they are not bird-hipped dinosaurs, or at least they are not ornithischian dinosaurs. Um, so ornithischian dinosaurs are one of the two main lineages of dinosaurs, and they are the one that does not include birds. The other main group are the saurischian dinosaurs, or quote unquote lizard-hipped dinosaurs, which do misleadingly do in fact include birds. Um, and the reason for that is convergent evolution. So, during the course of their evolution, some of the saurischian dinosaurs, specifically some of the theropod saurischian dinosaurs, evolved a hip structure that ended up looking a bit like those of ornithischians. And so you ended up having some saurischian dinosaurs with bird-like hips, including the modern birds. However, they are a distinct lineage from the um, dinosaurs that are actually named after the bird hip structure, and these are the ornithischian dinosaurs. And yes, because I'm sure this will come up, um, there is controversy over whether the classification of dinosaurs into these two distinct lineages is valid. Um, a number of years ago, a big study came out that suggested that, in fact, the ornithischian dinosaurs are more closely related to a particular group of saurischian dinosaurs called the theropods, and with the sauropodomorph dinosaurs, which are the other main lineage of saurischian dinosaurs, being more distantly related. Um, and that's still a subject of controversy, I would say. But the majority of recent studies that have been done on early dinosaur evolution seem to tentatively favor the traditional split into ornithischians versus saurischians. So, for the purposes of this story, I will be like referring to them in that way, with the traditional ornithischian versus saurischian split. And I would add that this study actually also supports the traditional split as well. Um, so, yes, for the time being, we're going to tentatively go with that, knowing that it could be wrong, depending on future studies. However, when it comes to the relationships inside the ornithischian dinosaurs, how the different ornithischians are related to each other, um, things have been, for most part, relatively stable. Nonetheless, there have been some points of controversy have arisen from recent studies. Um, so I guess before we go on, let's talk about which dinosaurs are ornithischians anyway. If birds are not ornithischians, then what are? Well, the ornithischian dinosaurs mostly appear to have been primarily plant-eating dinosaurs, and so they include a large number of different plant-eating groups. And so one of these groups is the armored dinosaurs, or the Thyreophora. So this includes the stegosaurs and the ankylosaurs. So both of these groups are probably groups you're very familiar with if you like dinosaurs. Stegosaurs are the ones with the plates kind of running down their back and spikes on their tail. And ankylosaurs are the ones that are really heavily armored. They're like covered in armor all over their bodies, in some cases even their eyelids, and in some of them they have armor forming a club-shaped structure on the end of their tail, probably used in defense, but also probably for fighting each other as well. And in fact, we have some recent evidence that this is the case, where we found specimens of ankylosaurs with injuries that may have been caused by these tail clubs. Another major group of ornithischians is the ornithopod dinosaurs, the so-called bird-footed dinosaurs. But again, they don't really have much to do with birds. That is a misleading name. Um, and the ornithopod dinosaurs, the best known ones are probably things like the duckbill dinosaurs or hadrosaurids. So these dinosaurs um, do often have a fairly long and wide snout, a little bit like a duck's bill. Um, However, if you saw one in real life, it probably would not have looked that duck-like to you, because the keratin on the end of the snout, forming a beak, would have created a sort of overhanging structure that made the tip of the beak kind of curve downward in a way that's not very duck-like. And so duckbill dinosaur is kind of name as well, but that is what they are popularly called. Many of the duckbill dinosaurs had these crests on their head. You might recognize Parasaurolophus or Corythosaurus if you like dinosaurs. And in many cases, these crests were connected to the inside of the nasal cavity. So they basically were hollow on the inside. They were hollowed out by the nasal passages. And it is widely thought that these crests were used probably in vocalization in these dinosaurs, to basically kind of enhance their calls. And in fact, people have done modeling studies that have tried to figure out potentially, like at least vaguely, what these dinosaurs might have sounded like based on the shape of their crests, which is pretty cool. Some other groups of ornithopods include things like iguanodon is another very well-known one, as well as a number of small two-legged things like Hypsilophodon, for example. And so basically, ornithopods consist largely of various small-bodied two-legged forms, and then bigger ones that probably mostly walked on four legs, like the duckbill dinosaurs and iguanodon, but could still walk on two legs as well. Um, and then the third major group of ornithischians is the Marginocephalia. And so this group of dinosaurs includes things like the Pachycephalosaurs, which are the dome-headed dinosaurs, which are generally thought to have used their thickened skulls for fighting each other. Although exactly how they fought, and in some cases whether they really fought in this way, is still debated. Um, and also the ceratopsian dinosaurs, which are the so-called horned dinosaurs, even though not all ceratopsians technically have horns, or these very obvious horns, but most of them at least have small horns projecting from the sides of their cheeks, as well as a parrot-like beak. And the later and larger forms evolved gigantic frills kind of projecting from the back of their skull, as well as much bigger horns projecting from above their eyes, and in some cases on top of their noses as well. And so things like Triceratops, of course, is a very, very well-known ceratopsian dinosaur within the Marginocephalians. And so you had these three big, very well-known groups of ornithischians, and pretty much all studies on their phylogeny have agreed that the ornithopods and the Marginocephalians together are more closely related to each other than to the thyreophorine dinosaurs. And that much is pretty much not controversial. But when it comes to some of the smaller and more obscure groups of ornithischians, there has been a lot of controversy as to their phylogenetic position. And so that is basically what this study wanted to address. So, uh, the way that the authors approached the study, I thought, was very well done, because what they did was they basically consulted all the previous phylogenetic data sets that have been used for studying early ornithischian phylogeny. Part of the reason there has been so much disagreement about the phylogeny of these different ornithischian groups is that people have used multiple different data sets to study their evolution. And so when you run these different data sets, you get different results sometimes, right? And that much is not too surprising. So, how do we resolve these disagreements then? Well, the approach that these authors took was that they consulted all the previous data sets and then compiled them into this massive, big single data set. And so they included pretty much all of the different characteristics that have been used in these previous data sets, and compiled them into a single list of characters. And in addition to characters that have been used by previous studies, they also kind of added some of their ideas for additional characters that people had not considered before. Um, and so this gave a very, very thorough list of anatomical characters of ornithischians. Um, and the way they did this, of course, was not just like willy-nilly, like kind of glomming all these different characters, all these different data sets together, right? Because, of course, even though these data sets use different characters, they also use some of the same characters. And so you don't want to like repeat using the same character over and over again. That's not going to give you a reliable result. And so they really went through and combed through these character lists and kind of compiled a list that was like including all of the characters that have been considered before, a few new characters that had not been considered before, and making sure that there were no repeat characters being used. And in the end, they came up with a list of over 940 different anatomical characters, which is extremely impressive. With a data set where you're working only with morphological characters and not genetic characters, because morphology is always all we have with ornithischian dinosaurs, there aren't any around
Mm.
today after all. Um, 900 characters is a lot. Like, this is a massive, massive phylogenetic data set. Um, and they included in this data set like um, over 170 different species of reptiles, mostly ornithischian dinosaurs, of course, but also other types of dinosaurs as well as a few different types of reptiles that were closely related to dinosaurs, um, and kind of entered them all into this big data set to try and figure out what is the most likely phylogenetic relationships of these ornithischians based on all these different characters that people have considered. Obviously, this is not going to be the last word on the subject because people are always going to find new discoveries and come up with new methods of analyzing the data. But I do think that this is definitely like the most thorough job of ornithischian phylogeny that has been done to date. And so, if you want to consult like any individual study for what is the most likely phylogeny of ornithischians, I think this, at least for a while, is going to be like the go-to study. And any future study that uh, wants to work on this topic is going to have to go back and consult what this study did and kind of see if they can build upon or improve on it. This is like a big, massive deal when it comes to this topic. Like it's a landmark study. It's like one of those studies
Mhm.
that is going to get consulted over and over and over and over again in future research. Um, so let's see what they found regarding these controversial areas of ornithischian phylogeny. Now, of course, they found a lot of different results, and we are not going to have time to go into all the nitty-gritty little details. So I'm just going to do a highlights reel here. First notable result that they found was that a group of, or I should say, a series of Triassic reptiles seem to be very early members of the Ornithischian dinosaurs. And this is a massive deal because one of the big questions in Ornithischian phylogeny that we had, or Ornithischian evolution in general that we had before this, was that where are the Triassic Ornithischians? Because we know dinosaurs originated in the Triassic, and we have plenty of Triassic saurischian dinosaurs, so theropods and sauropodomorphs, as well as a few early groups of saurischians that probably don't belong to either theropods or sauropodomorphs. Um, but there were almost no definitive Triassic Ornithischian dinosaurs. In fact, there was only one that was at least widely considered to be um, a Triassic ornithischian called Pisanosaurus from South America, but that was the only one. And basically, there were no other Triassic ornithischians definitively known. Um, that being said, there were a well, let's call them a group for now. A group of Triassic reptiles called the Silosaurids that were very dinosaur-like, um, and had a few ornithischian-like features. For example, the tip of the lower jaw in Silosaurids was toothless, and this is also the case in ornithischian dinosaurs as well. In fact, one of the main distinguishing features of ornithischians compared to saurischians, and probably an even more reliable distinguishing feature than the hip structure, is the fact that they have this extra bone on the end of the lower jaw that doesn't have any teeth in it, but was probably covered by a beak. And so pretty much all ornithischians would have had a beak on a lower jaw. Even though the back part of the jaw often did have teeth in it. Um, and Stylosaurids had this kind of feature as well, but in other ways, they didn't seem a lot like early true dinosaurs. And so a lot of earlier analyses place dinosaurs as being close relatives to dinosaurs, but not true dinosaurs themselves. Um, However, it had been suggested because of like their ornithischian similarities that, you know, what if silosaurids were the Triassic ornithischians that we were missing all along? And a few other previous studies on this had found this particular result, supporting silosaurids as early ornithischians. Um, but like most of these studies were not focused specifically on ornithischian phylogeny. And so it was just kind of a interesting result that popped up every now and then. People were like, yeah, I can see why that might be the case, but we're not necessarily convinced just yet. And of course, like I said, this is not the last word on this particular topic. Um, but the fact that this study also supports this result, kind of independently of the previous ones that did so, suggests to me, at least provisionally, that this may very well be like the most rigorously supported position for the Silosaurids as of this moment. And if this is the case, then we do have to rethink kind of our idea of what like the earliest dinosaurs were like a little bit. Previously, I was very kind of hesitant to refer to the Silosaurids as a group, and that's because, in part, because of the results of this study. And what they found was that the Silosaurids themselves, they don't all form like a unique lineage that is separate from all of the other ornithischians. Instead, they form kind of a series of lineages leading up to the rest of the ornithischians instead. And so, technically speaking, the only member of the group Silosauridae should really be Silosaurus itself, whereas all the other things that are were formerly considered Silosaurids are technically not members of this group. But yeah, so we can say that quote unquote Silosaurids form like a series of Triassic ornithischians going up to the rest of the ornithischians, like the traditional idea of ornithischians. But it's very cool that this study supported that idea. Um, Now, if we go into like the remaining ornithischians, and there's one particular group that has been quite contentious in recent studies, and this is a group called the heterodontosaurids, which we actually have talked about in this show before, in a previous news episode, about a new specimen of Heterodontosaurus, which is one of the best known heterodontosaurids. Basically, what it tells us about the breathing apparatus of early ornithischian dinosaurs, which is very cool. So we were talking about dinosaurs and breathing, and that's that episode as well. See, it's all connected. But in any case, um, heterodontosaurids have been very contentious in ornithischian phylogenetics because it has been debated about exactly where they go. They seem to have been around very early on. Um, like we have fossils of them all the way from the early Jurassic into the early Cretaceous. And the majority of recent studies, I would say, have generally found them to be kind of like one of the earliest groups of ornithischians to have appeared. And so they're outside of a group like that contains things like the armored dinosaurs and the marginocephalians and the ornithopods, the big three that we talked about earlier. So they're kind of outside of the group containing the main, more famous ornithischians. But some recent studies have suggested that maybe heterodontosaurids are not this kind of early branching group, but instead a type of marginocephalian, which is quite an interesting idea, but it's definitely not crazy, and in fact not a completely new idea, because early on people had suggested that maybe heterodontosaurids had something to do with marginocephalians, because some of the features in their skull do look like early ceratopsians as well as pachycephalosaurs, especially things like heterodontosaurs had these weird fang-like teeth, like almost like canines almost, and a lot of the ceratopsians, and especially early ceratopsians and pachycephalosaurs, had these as well. Um, and this would solve another gap in the ornithischian fossil record because we only have pachycephalosaurs in the Cretaceous period, but not in the Jurassic, even though we do have Jurassic ceratopsians. And so if these two are closely related, then we know there must have been Jurassic pachycephalosaurs somewhere, right? But we don't have any right now. So where are they? Well, some people suggested maybe the heterodontosaurids were the Jurassic pachycephalosaurs. Um, And while that may have seemed plausible in some respects, this study does not support that idea. This study supports the idea that Herodontosaurs are like this early group that are not especially close to like any of the big three ornithischian groups, and so it supports that more traditional conception, which is fair enough. I do think it makes sense considering like the time frame that we know them from. Um, when it comes to the big three groups, there are a number of interesting things we could discuss, but I would say that one of the main points of contention in recent studies is that what is an ornithopod anyway? So, yes, the duck-billed dinosaurs and iguanodontians, they are ornithopods. Like, that is not controversial. But the controversial part concerns a lot of the small bipedal ornithischians that we know of. Because traditionally, a lot of these small bipedal ornithischians have like pretty much automatically been classified as ornithopods. It's like you're small bipedal, you don't have armor or horns or anything special like that. Then you must be an early ornithopod. Like you done, if you go to like old dinosaur books, you will see the term Hypsilophodontids, and the term Hypsilophodontid was used to encompass a bunch of these small bipedal ornithischians. Um, but it turns out that these small bipedal ornithischians are actually very diverse, and a lot of recent studies have suggested that many of them are probably not true ornithopods after all. Um, in fact, the heterodontosaurids were once considered part of this kind of big assemblage of hypsilophodontids, but of course, later studies have shown that they're almost certainly not like ornithopods, and don't really have much to do with them. Um, and that's been the case for many other types of small bipedal ornithischians. Um, in particular, there's a group called Thescelosaurids, which we have talked about multiple times on this show, surprisingly. And I know you have mentioned before that they're some of your favorite dinosaurs. Um, and indeed, there's been this big controversy about whether they are ornithopods or not, because some recent studies suggest that they are actually outside the group containing marginus cephalians and ornithopods. And so Thescelosaurids might be closer to ornithopods than to thyreophorans, but not like true ornithopods themselves. But other recent studies suggest they are true ornithopods, just like a kind of early branch coming off of them. Which one is the case? Well, um, this particular study suggests that thescelosaurids are not true ornithopods. The thescelosaurids are quite interesting because even though they don't look very spectacular, we have evidence that many of them dug burrows. At least some of them dug burrows because some of them have actually been preserved in burrow structures. Um, and they do exhibit some anatomical features that suggest they dug burrows. So they were kind of like the dinosaur version of like rabbits or something like that. Now, some of them could get pretty big, actually. Like Thescelosaurus itself was something that's up to like 4 or 5 meters long, something like that. So definitely much bigger than a rabbit. And indeed, it is unclear whether Thescelosaurus itself was a burrower. But I know we have actually discussed this on the show before. It does have some features that suggest that it either might have dug burrows or was descended from burrow digging ancestors. Um, and so, yeah, that's quite an interesting aspect of their biology that we don't see very often in dinosaurs. We don't have evidence of burrowing in most other types of dinosaurs, other than some types of birds, really. So they're a very cool group. I quite like them. Um, and within ornithopods, there's also been a lot of controversy beyond what actually counts as an ornithopod. So, for example, if a lot of these small bipedal things are not true ornithopods after all, then what are Hypsilophodontids actually? Um, well, it turns out that Hypsilophodon itself, which has been known for a very long time and is often pictured in like dinosaur books, um, in this study is found as a true ornithopod. Um, and it turns out that this particular study does find one close relative to it, and that is a Spanish form called Gideon mantelia. Hypsilophodon itself is from the UK, by the way. Um, Hypsilophodon and Gideon mantelia form the group Hypsilophodontids in this particular study. So it turns out that Hypsilophodon does have at least one buddy, at least according to these results. But yeah, the group Hypsilophodontidae has been greatly diminished since the traditional classic days. If you go back to old dinosaur books where they talk about the group Hypsilophodontids, yeah, almost none of those dinosaurs other than Hypsilophodon itself is actually a member of Hypsilophodontidae. Um, if we go up into the bigger ornithopods, the group Iguanodontia, which includes both dinosaurs and iguanodon and such, there is a group called the Raptidontomorpha, which has mostly traditionally included species found in Europe. Um, and so these particular iguanodontians have like these very robust jaws. The species is found in Europe, at least. Many of them are interesting because they seem to have been what we call insular dwarfs. So they lived on islands, and so they became kind of smaller bodied than their ancestors were. Like classically, like definitive raptidontomorphs were only known from Europe, although there was an Australian ornithopod called Muttaburrasaurus that has sometimes been considered a member of this group, which would be really weird, right? Because it's like how do you suddenly have like this single Australian form like out in the middle of nowhere, whereas everything else was in Europe? This study does not suggest that Muttaburrasaurus is a raptidontomorph. We'll get to what it actually is in a second. Um, However, Raptidontomorpha does not only include the European forms in this study, but also some North American forms, including a species called Tenontosaurus. And Tenontosaurus is mainly known in dinosaur books for being the potential prey item of a raptor dinosaur called Deinonychus. So if you see Tenontosaurus in dinosaur books, it's almost always getting gobbled up or attacked by a group of Deinonychus, and that's because there are fossil sites where we have found Tenontosaurus being preserved with like multiple different specimens of Deinonychus, where it's given rise to the popular image that Deinonychus was hunting in packs to bring down Tenontosaurus, which has been controversial in recent years. But this is not the story for that. Tenontosaurus is actually a very interesting dinosaur beyond its association with Deinonychus, because it has like, this really long tail that gives it a very distinctive shape. It's a big shame that it's not better known for like what it looks like, and instead of like what things ate it. But anyways, Tenontosaurus, as well as like a smaller, like two-legged form called Convolusaurus, relatively recently named form, were also found as North American representatives of Raptidontomorpha. Um, and so that's pretty cool. So it turns out that this group might have spanned both Europe and North America. And we know that these northern hemisphere continents were like intermittently connected during the Cretaceous period. And so it's not so crazy that you would get this group distributed across like these land masses. It makes a lot more sense than having like this one Australian form. But okay, so if this study didn't find Muttaburrasaurus as a raptidontomorph, then what was it anyway? Well, as it turns out, that this study found Muttaburrasaurus as a member of a different group of iguanodontians called the Elasmaria. And Elasmaria is interesting because almost all of the different southern hemisphere iguanodontians, other than duck-billed dinosaurs, appear to be members of this one group called Elasmaria. As it turns out, that in this particular study, it was found that Muttaburrasaurus might also be an elasmarian, which would make more sense than it being a rapidontomorph from a biogeographic perspective. And Muttaburrasaurus, if it's an elasmarian, would be a pretty cool one because most elasmarians that we found are relatively small-ish and they kind of retain this sort of typical early bipedal ornithischian body plan. Although we are starting to find some weird ones lately. Like there was a recently named one called a Chalkysaurus, where there's evidence that its tail was kind of curved downward in a sort of S shape. Very weird. Um, but anyways, most elasmarians, from what we know about them, don't seem to have been too like spectacular looking. But Muttaburrasaurus was pretty good sized. Like it was 6 meters long or somewhere in that range. Um, and it's got like this really tall, like arched nose and very strong jaws. So those very robust jaws were part of the reason why it was commonly considered a rapidontomorph in previous studies. Um, but anyways, a very cool looking dinosaur, and probably one of the best known like Mesozoic dinosaurs from Australia. Um, and so, yeah, those were some of the main findings that of the study that kind of clears up many of these major controversies that have been occurring in ornithischian phylogenetics. That being said, as I said, there is a lot going on in this paper. You can tell just by the figure here, like you basically can't read it because they include so many different species. And so, if you really want to get a better sense of what this paper says, then I strongly encourage you to go and read the details for yourself in there. But yeah, I really like this study. Like I said, I think it is like a really great example of kind of bringing together all the available data that we have to investigate this problem. Um, as someone who studies morphological phylogenetics myself, I study birds, but we use very similar methods and ideas. it takes a massive amount of effort to assemble a data set this big and this thorough. So I am very, very impressed by the authors for like pulling together such a massive, massive project. Like I said, I really think this sets like a new standard for um, studies of ornithischian phylogeny, and I look forward to seeing how this develops in the future. I guess, as I mentioned, because it's hard to read the figure here, I should probably go through it just so you know like what goes where, right? So if you start from the top, like the green section on the top, those are the silosaurids. Like I said, they don't form a clade, an individual lineage in this particular study. So they're basically a series like leading up to the rest of the ornithischians. The next box down are the heterodontosaurids in the yellow. The next group are the armored dinosaurs, the thyreophorans. Um, and then we get another green box, and those are the thescelosaurids, so they're outside of like both marginocephalians and the ornithopods. Um, then we get the marginocephalians split into pachycephalosaurs, which are in like kind of an olive or dark green on top, versus the ceratopsians, which are in orange. Um, and then we have the various different groups of ornithopod dinosaurs. So you have like Hypsilophodontids as a small group in orange. You have Rapidontomorphs in a sort of teal color. Then you have Elasmarians in red. And then sort of pinkish purple color are a group that we didn't really talk about called the Dryosaurids. And finally, we have like the later Iguanodontids. So the things like Iguanodon and duckbill dinosaurs would be in like part of this dark blue part of the tree on the bottom. And so that's the structure of the Ornithischian family tree as of now. So, do you have anything to add to this?
I guess. Well, I mean, for one thing, like amazing coverage. I mean, it's really neat to see a study like this that's so thorough and uses so many characters. Um, do you think like I mean I don't want to say this is like this would be the last word, but like do you think like we have the big main structure pretty much in place now?
That's a really good question. I would say at least as of now, I think this is probably pretty close to as good as we're gonna get, like until we like get more data. I will say that there are probably some other ways in which the data set could be analyzed, because I think the authors only analyzes on using the maximum parsimony method, which we've discussed
Mm,
before on the show. We don't have to go into like the details of different methods right now, but there is a lot of controversy about like what are the best methods to use when it comes to analyzing morphological data for phylogenetics. And so I would be really interested to see if these results still hold up if they use something like the Bayesian method, for example. And one of the cool things about the Bayesian method is that you can incorporate things like data on the ages of these different dinosaurs. And sometimes that can influence the structure of the tree. And so, yeah, I would like to see like this data set being run under a Bayesian method just to see if, like how different it gets. But yeah, like other than that, really, I think this is probably like, pretty darn close to being the definitive version of like ornithischian phylogeny for the time being.
gotcha. Okay. I guess my second biggest, I guess, observation of from this like this paper, the tree that I'm seeing here. Now the tree on display here, is this correlated with geologic time?
Yeah, so they did like kind of put all the different species like according to like their different time periods on this tree. Yes. So it is scaled against geologic time. But I just to clarify because I mentioned this um they did not use the ages to kind of reconstruct the phylogeny. Whereas if you ran a Bayesian analysis, that is an option you could choose, is to actually tell the analysis include information about the ages to determine where these things go, basically. Whereas this is like they already have the tree, and so they plotted it against time kind of separately. So yeah, that's kind of the distinction there.
I see, because one thing I've really noticed is there are still quite a few gaps, I guess, in the fossil record for many of
Absolutely,
these
yes.
groups. Like I'm looking at the thescelosaurs and the hypsilophodontids and the uh, elasmarians and so forth, and like it's interesting to see like there's these huge spans of time where we don't find members of these lineages, and
Hmm.
then suddenly there's just quite a few of them. Um, so I guess I wonder if like finding earlier members of those groups might tweak the data a little bit or maintain the same model. Um,
Hmm. Hmm.
that I think I'd be very curious to see, right?
Yes.
Where are the Jurassic Thessalosauриds?
Hmm.
Yeah, this is a very impressive study, and I'm very pleased to see this out. And I mean, obviously, like the results of the Silosaurids in parentheses, essentially being like definitely a new group of dinosaurs to consider when talking about dinosaur diversity is really exciting to think about. I mean, I remember first learning about these animals, and like they were, you know, dinosauromorphs. Like they were on the
Hmm.
way to becoming dinosaurs, and of course, like their placement in the phylogeny would affect like the postures and behaviors and ecologies of the earliest dinosaurs. And so, seeing them with the ornithischians now, I'm very curious, like how that understanding will change for the dinosauromorph radiation before dinosaurs.
Yeah, absolutely. So yes, you definitely raised some very good points there, and certainly I think finding early members of a lot of these groups would be like one of the main things I would like expect to potentially kind of change the results of these of a bit because yeah, those early members they tend to be very important to our phylogenetic reconstructions because they show what the actual ancestral like conditions were like for all these different groups. And so, as you mentioned, that we clearly do still have a lot of gaps here. Like we don't have Jurassic Thescelosaurids or Jurassic Pachycephalosaurs still. So hopefully we can fill in those gaps with future discoveries. Um, and one last thing I'll mention, because we have discussed this on the show before, is a dinosaur called Changminya. We mentioned this dinosaur back when it was newly described as one of our news stories. That was quite a while ago, actually. And it's known for like this really beautifully preserved skeleton from the early Cretaceous of China. Um, and at the time, I think we were saying that it was considered an ornithopod, an early ornithopod by the authors. But we did mention like the controversies about how we weren't sure which dinosaurs were actually ornithopods and which weren't. And well, this study included Chongminia, and as it turns out, this study suggests that it is a Thescelosaurid. So in this study, it is not an ornithopod. Yeah, that's a pretty interesting to get that follow up there. But if you don't have anything to add to that, we can continue with your second story and our final story of this episode.
Certainly, yeah. And we're going to take things a little bit differently for a change because I'm happy to report that this is another botanical story for
Hooray!
our channel. So, this is a review paper by Robert J. Morley of the University of London. So, in botany, the plant communities and habitats of the world have been classified into floristic kingdoms, or phytochoria, and this is similar to the zoogeographic realms in zoology. Basically, these are areas of the world where the floral components are unified by similar species and higher clades, often through environments that share a common ancestry through evolution, colonization, and dispersal. Generally, although the schemes vary, about six of these have been delineated. So there's a Holarctic kingdom, which encompasses North America and northern Eurasia from the polar north and across the temperate regions and into North Africa. The Neotropical kingdom, which is tropical North America and all of South America. The Australian kingdom, which also includes New Zealand and other Oceanian islands. The Antarctic kingdom, because yes, that continent also has land plants. The Cape kingdom, which is strictly on Africa's Cape. And the focus of this paper, the Paleotropical kingdom, which encompasses most of Africa, of course, except the Cape in the far north, India, and Southeast Asia. This region contains a vast array of ecosystems, including tropical grasslands, dry deciduous forests, wetlands, and deserts. And of relevance to us today, closed canopy evergreen tropical rainforests. Now, these types of rainforests have tree cover that forms almost an umbrella over the lower vegetation, blocking out as much of the light as possible as the trees are competing for the best solar rays, as well as having tree leaves that do not fall off the branches during the cooler, dry seasons. In the present day of our wonderful Holocene epoch, the paleotropical rainforests are found in a few selected patches between the Tropic of Cancer and the Tropic of Capricorn. In Africa, the Congolese region hosts lowland rainforests that only grow where rainfall is highest for most of the year, typically 63 to 80 inches annually. And it's a highly diverse landscape as far as wild animals are concerned, but compared with Southeast Asian rainforests, the diversity of plants are far lesser than you'd think. The main trees that grow here belong to the legume clade, that's Caesalpinoideae, which includes the peacock flowers, while the understories are dominated by lianas, orchids, and ferns. On neighboring Madagascar and the nearby islands like Mauritius and the Seychelles are the Indian Ocean rainforests, which have a far greater diversity and include more endemic species of plants and animals, as per the laws of island life. These rainforests exist within a substantial range of elevations, from sea level to 9,000 feet, and so different areas can have a lot of rainfall and include 130-foot canopies, or have little rainfall and so only reach almost 10 feet up. Now, in South Asia, the Indian subcontinent, the tropical rainforest characteristic of the Jungle Book are only found along the western edges. These lowland, semi-evergreen, and montane forests share similar floras with those of Southeast Asia, in that they're dominated by trees of a clade called Dipterocarpaceae, that is, the two-winged fruiting trees. Keep that in mind for later. These trees, of course, their seeds contain long, flattened structures that guide them in the wind away from their parent trees. Now, these dipterocarps include luans, hopias, rhesocs, and many more varieties. The tropical rainforests of southern Eurasia are some of the tallest in the world, reaching up to 230 feet, and also include plants like palms, figs, legumes, myrtles, laurels, and mahoganies. Now, these rainforests aren't always well watered, but the monsoon season does do much to keep the dry away. Now, let's move to the next slide here. Uh, One of the curious aspects about the Paleotropical kingdom is that, unlike other floristic kingdoms, its constituent floras are separated by barriers on three separate landmasses, if we want to consider Southeast Asia as Sundaland, that had been separated on and off for many millions of years. So, when had the Paleotropical rainforests come to be, and how did they spread around the kingdom, and from where? Robert J. Morley decided to review the current evidence for the deep time of the Paleotropics, mainly utilizing data from plate tectonics and paleoclimatology, as well as a sampling of 11 of the oldest known fossil sites that include pollen from rainforest trees. We know from plate tectonics that the northward spread of the Indian subcontinent influenced Africa as well as Eurasia because it raised elevation towards the Horn of Africa, allowing island chains to spread plant floras eastward towards India. And once India was connected to Eurasia, plants could continue to move eastward towards Southeast Asia. Now, starting with this logic in mind, Morley discovered that the oldest rainforest pollens dated specifically from Africa 80 million years ago, during the Campanian age of the late Cretaceous epoch. From there, the sites grow younger and younger towards South Asia, then Southeast Asia, and then on to Oceania. And now this is a very important understanding because there has been a persistent claim that tropical rainforests are especially old ecosystems,
Hmm.
like on the order of at most 150 million years old, going back to the Jurassic period. But the data clearly does not support this. In fact, it shaves that off by over half that time. So, looking through the literature from there, Morley was able to trace in fairly great detail the origin, evolution, and dispersal of closed canopy evergreen rainforests across the Paleotropics. So let's jump to the next slide now, and we'll see that summarized here on this slide with some wonderful infographics here. There are many similar clades of rainforest plants between the Neotropical and Paleotropical kingdoms, which suggests a shared common Gondwanan ancestry. Thus, if the earliest African rainforests are about 80 million years old, then that was around the time that the two floristic kingdoms diverged from each other. The dipterocarp clade is represented in fossils at this time from seasonally wet environments, the earliest being from the Maastrichtian of Sudan. making them some of the oldest paleotropical rainforest plants still represented today. As stated beforehand, the Indian subcontinent was rapidly drifting northwards towards Eurasia at about this time, and by the latter Maastrichtian had reached the equator and began developing a tropical climate, as indicated by plant fossils from the time. As the land masses started colliding, India seems to have hit an island chain that has been named in the literature the Kohistan-Ladakh Island Arc, which was oriented towards the Horn of Africa and already sported a tropical climate. Thus, it's from the Horn and across the island arc that the paleotropical rainforests started to spread eastwards to island India. Now, this transition has been dated to 66 million years ago and continued into the Cenozoic era, Paleogene period, and Paleocene epoch. So, remarkably, these are forests then that not only survived the Deakin Traps eruptions, but also the greater KPG mass extinction event.
Mm.
Now, given that dipterocarp trees are frost-sensitive megathermal plants, I think this is something that is worth investigating, just how plants like that could have survived such a destructive end of the world as that.
Mm.
Now, one fascinating result of this ecosystem dispersal is that today Sri Lanka contains the last remaining refugia of late Cretaceous age rainforest plants,
Oh, wow.
like the dipterocarps of the genera Stimonoporus and Shorea. And of course, that has conservation implications. Now, unfortunately, paleotropical rainforests would eventually wither away from much of Africa as the continent dried during the latter half of the Cenozoic era. And in fact, the dipterocarp trees mostly died out from this part of the world by the Pliocene. Going back in time again, thus we briefly entered the discourse of the out of India hypothesis, which was discussed prior with late Cretaceous spiny feather palms during our February 2024 news episode. According to that hypothesis, the main mode of dispersal for plant species was right when India made full contact with Eurasia and in that direction, with very little dispersals from Eurasia into India. And indeed, according to the data that Morley gathered, it was from India that paleotropical rainforests arrived in Eurasia and then continued eastward into the southeast. But it was less simple as it sounds. Morley counted two main dispersals from India into Southeast Asia of these environments via present-day Myanmar as far as Sulawesi, and this was during the earliest Eocene epoch, which prior to this time contained a very low diversity of Laurasian-type flora, despite having the exact same climate as India and equatorial Africa. And the dating points to the earliest establishment of Southeast Asian rainforests is thus at 48 million years ago. But the story does not end there, however, because Southeast Asia would experience far more changes to its paleotropical flora through the Oligocene and Miocene epochs. Sundaland, which is today represented mainly by islands of various sizes, slowly formed as the Australian plate moved northwards and pushed previously seasonally dry monsoonal environments towards the equator and so developed them into equatorial tropical environments, which could be better established for paleotropical forests flourish. And of course, these would, of course, eventually replace the Laurasian-style floras. And so by the Miocene epoch, dipterocarp forests were firmly in place, where they became the dominant tree groups in the region. Now, when looking at the easternmost regions of the Paleotropics, those which border Oceania and the Australian kingdom, we find a much more varied diversity of plants. For example, in the more montane forests, the vegetation shares species and similarities with Australian rainforests, which is evidence of a past Sahul-Sunda floristic exchange. Now, according to the data, New Guinea first arose from the drifting of tectonic plates during the Miocene epoch and reached its current position by the Pliocene, but fascinatingly had a mostly Eurasian flora originally, with a scattering of Australian genera like Nothofagus, indicating that dispersals were mainly from the west and not the east in the beginning. But it must be stated that throughout this time, and as some records suggest perhaps even since the Eocene, Pacific elements had filtered and dispersed into the floristic kingdom from the east, almost paralleling the spread of animal species across Wallace's line between the Australian and Indo-Malayan zoogeographic regions. So it is that by 15 million years ago, the paleotropical forests of easternmost Southeast Asia were present. And so it is that the evolution and spread of the paleotropical rainforests was mainly facilitated by the movement of tectonic plates and the opening of favorable climates. And I think studies like this underscore some important points about deep time. For one thing, environments do not just change from dry to wet or from
Mm,
cool to warm in a vacuum. Often they move about into new territories when climatic and geological opportunities open. While paleotropical forests managed to survive in the Congolese region of Africa, it was indeed the movement of India into Southeast Asia that ultimately saved the Great Diptera carp forests from total extinction. And of course, as I've mentioned, today they make up the most diverse trees in the widest range of the southern Eurasian rainforests. On another front, while rainforests are no doubt old environments, they're not as ancient and unchanging as they look.
mm,
Clearly, from reviews like this, we know that modern type tropical rainforests have not been around since the Jurassic period. They're only late Cretaceous in origin, latest Cretaceous in origin. And even most of the rainforests of southern Eurasia were not in place until the Oligocene and Miocene epochs. They're remarkably young in these cases. And lastly, I think by showcasing studies like this, it helps to bring a more holistic picture to the history of life on Earth
mm,
because it doesn't just highlight animal evolution or even the specific evolution of certain plants, but environmental evolution,
mm.
which I've often found is underrepresented in most of the surveys of deep time that I've certainly read, beyond maybe highlighting the spread of grasslands in the later Cenozoic at the expense of forests. And for that, I am grateful to see the work of Robert J. Morley illustrated so beautifully here, and I hope I can cover similar papers in future episodes. And so that's my second news story. I'd love to hear your thoughts about this.
Yeah, wow. What an amazing overview. Like that's yeah, I think with tropical rainforests, they're an ecosystem that is just so inherently fascinating to those of us who like natural history, right? Because I mean, after all, that's where most of the modern biodiversity is. So how could you not love them if that's a topic you're interested in? The fossils are interesting because this is one of those things that also keeps us up at night because in general, tropical rainforest environments are not very good for preserving fossils. Like there are just so many things in rainforests that anything that dies just gets gobbled up almost immediately. Um, and also, the soils tend to be very acidic, and so that is also not very good for preserving dead bodies of many types of organisms. Um, but nonetheless, evidently we do have enough fossil sites of the plants at least with the plant fossils to determine at least the presence of rainforests in some areas and time frames. I really would love to know like what what types of animals were living in some of these ancient rainforests, because as far as I know, we do not know very much about that side of things. But yet we know that tropical rainforests are the hotspots for biodiversity in present day, so there must be so many things we're missing. Um, I guess something else that came to mind was regarding the question of how rainforest plants, these paleotropical plants, survive the KPG extinction. That is a really good question, and um, to my knowledge, it is generally suspected that many different plant species survive the KPG um, through their seeds, essentially. Um, because it is thought that a lot of the mature vegetation was destroyed during the KPG extinction event. Like a lot of it was burned up by global forest fires, pretty much because of the like burning hot debris that rained down from the sky when the in the wake of the asteroid impact. Um, and so it is quite likely that a lot of plant species made it through by remaining dormant as seeds. And so now I'm curious, like how long can a lot of these rainforest trees remain dormant? I mean I don't know off the top of my head. But that would be something interesting to investigate. Um, all the studies we picked today, like all have this thoroughness to them that makes them very satisfying. I quite like it. So no, there's very cool study once again. I agree with you. Like it's great to cover plants more. It's great to cover like ecosystem level topics more. So this study definitely fulfills both of those for sure.
Absolutely. And it also like leaves you wanting more, even with the thoroughness, because I must emphasize again that the Paleotropics does not just include the rainforests. I mean,
Mm.
there are deciduous forests, there's grasslands, there's deserts. How did those change over time? I mean, those are other fascinating stories that we could tell, and I'm sure the literature is there to bear this in mind. Or maybe not. Maybe these are areas of new research that we really got to start digging into. It certainly keeps me excited and keeps me motivated to keep sharing these wonderful stories with everyone here. Um, and yeah, like that's about it for us today. Yeah, really great stories. Really happy to have been able to share them all with you. Um, unless there's anything else you'd like to add, would you like to go ahead and jump into our main acknowledgments?
Let's do it.
Alrighty. So moving on to the next slide. Of course, we are on Patreon. That is patreon.com/time and clades. Patreon is a website service where people can log in and they can make an account. And if they so choose, they can leave monetary donations of a certain variety and keep up with content creators as they develop their shows or what have you, or projects. And so for us on Through Time and Clades, we are always giving updates on upcoming episodes, what stories we want to pick when we meet up to talk about them, sneak previews and opportunities to ask questions. And so there are tiers available that can allow you to experience some of this content. And in fact, we have tier systems that you can even get shout outs at the end of each episode. And so we have quite a few people already that are owed shout outs at the end of each episode. So we definitely want to thank my sister Julie and our good friends Paul, Denver, Tristan, Frankish, and Val de Nunzio for their contributions and support. It really means a lot. And any contributions at all help us continue the series and develop new projects and expansions. And so moving on to our general acknowledgments, of course, we want to thank our friends Henry and Alicia for their contributions to the series. Henry's responsible for the wonderful theme music that opens each episode, and Alicia is responsible for the color scheme of Albert's Alvarezor avatar. Cheerful little fellow. Moving on, of course, we're still on Twitter. We are at Time and Clade, where we generally drop in episodes as they release so they can be shared. But most likely you're watching this on YouTube on our page Through Time and Clade. So if you're interested and you want to like and subscribe and follow along for notifications, that's always appreciative. If you have any questions at all about the show, whether about the papers and topics we talked about today, or just anything in general, you have three ways to contact us. You can send us an email, timeandclades@gmail.com. You can tweet at us, or you can leave us a comment on our YouTube page, and we will respond in kind. Of course, if you want to check out the paper we covered today or any other things that we discussed, we will have links in the description to those references available to you today. And so, with that, that's the end of our show. We want to thank you all so much for joining us. Um, we're on a pretty good run at present. So I think it's safe to say that we might have a July episode to look forward to. Certainly, this month again is pumping out a lot of really great papers that are very interesting, and I
Yeah.
think it's going to be another difficult choice to pick which ones to include, because goodness knows this month we had some close calls that would have almost featured on this show. But alas, there were papers that were just a little bit more fascinating and a little bit more obscure that we wanted to give their just dues and highlights. So we hope to see you then, and take care. Have a wonderful rest of your day.
Take care, everybody.